Ajay, I'd like to send one more poll just to get to know
Sure.
who's here a little bit more. And this poll is just tell us about your work. And by work, I'm not asking about what research you've done lately, but more basic, where are you likely to run your simulations? I'm anticipating that the audience here is running simulations of OpenFOAM or GeoClass or other hazard relevant simulations, excuse me. So the question is, where are you running these simulations? Do you run them on your local computer? Do you run it at a university or a company cluster? Do you use cloud services like Amazon Web Services or Azure? Do you run things at DesignSafe? Or not applicable? You don't run simulations.
It is a really interesting poll.
Yeah. The next question is, do you have a DesignSafe or a TAC account? TAC is the Texas Advanced Computing Center, where DesignSafe is hosted. The next question is, how much does it cost to run simulations at DesignSafe? So this is a little bit, yeah, just curious to know what people's impressions are with respect to where they're running their jobs and costs. The fourth question, how many computer cores does your laptop or desktop have? There's no right or wrong answer to these last couple of questions. Well, maybe there is to the last question. The fifth question is, how many cores can you use at DesignSafe's Stampede 2 high performance computer for your research? The last question is, whose allocation, so whose computational resource allocation do you use when running SimCenter applications? So running HydroUQ locally on your desktop, it obviously is using your own computational resources. Running that job at DesignSafe, whose supercomputer allocation do you use? And I'll give some of these are hard questions, so if we just give people another 30 seconds to answer, Ajay.
Sure, definitely.
So a few more people need to vote, if you would. Try to get those answers in before too long so we can begin with Ajay's presentation, or share these results, and then move on to why we're here. Okay, I think that's about enough time. I'm going to end the poll. If you're trying to finish your last question, go ahead and do that. And I'd like to share these results. So the first question is, where are you most likely to run your simulations? Kind of consistent with what we see at in other tool trainings. A lot of people, right here we have 42% are running on their local machines. 25% use a university or a company cluster. And 4 people say that they use DesignSafe. So that's great. Do you have a DesignSafe account? 92% of us have one. That's wonderful. With that DesignSafe account, which is free and available to any researcher, comes at no cost and is available both to international and US-based researchers. So then a little trick question here. How much does it cost to run a simulation on DesignSafe? I'm glad that nobody chose that it costs dollars, and that more importantly, 75% of you answered correctly. It's available at no cost to natural hazard researchers because of NSF's NEARI funding. So I didn't cover that in the presentation of the introduction, but I'm glad to see that most of you agreed that it's due to NSF funding that opens up free computational resources to the research community. I'm not really so interested in the outcome of how many cores your computer has. Most of you said it has 6, but the underlying question goes to the next question, which is, can you use it DesignSafe? I would much rather use the 130,000 cores at DesignSafe for my simulations than the 4 or 8 cores that my laptop has to offer me. So I think that was an easy question, but the response that 3 of you prefer to run large jobs on your laptop, I would encourage you to explore the resources at our NERI partner, DesignSafe. And finally, whose allocation do you use when running SimCenter applications? The correct answer is that the SimCenter, you use the SimCenter allocation. Not only that, but it would be wonderful. We appreciate citing the SimCenter software and DesignSafe in your publications that result from that research. We do require you to log in to your DesignSafe account when you run our applications, but you're not actually running on your own computational allocation. You're using the SimCenter allocation, so you're not charged, at all to use our tools like HydroUQ. So thanks for those answers. And at this point, Ajay, I hand over the meeting to you.
Thanks, Matt. Thank you so much for the introduction into the session and giving everybody an idea about DesignSafe and the tools that are there at the SimCenter. I think that gives a really nice and holistic idea of what is being done at the SimCenter and how everybody can engage with the SimCenter and the NERI as well. I mean, one thing that I just wanted to say, since Matt was talking about the DesignSafe account, technically our tools can also be run on the university cluster with a because it uses an Agave API, which is an open-ended API, but you probably have to do a bit of work to set this Agave API with the university cluster, and then technically it can also be run. So I just wanted to put it out there that it's, even though we do want you to use DesignSafe, and I have no doubts on that, but there's also an option to use it with your own thing with a bit of work. I want to add that there, that it will take some work to set it up, which is already set up here nicely with DesignSafe. Okay, so I will not continue. I will not talk about much about NERI and the SimCenter. Matt already gave a very nice introduction, so I'll save some of these things. And also Matt talked about these puzzle pieces. Today and tomorrow, we will try to understand what these puzzle pieces are and how they're working together, particularly when we look at the HydroUQ application and see what is happening in here. So the most important thing that I've seen is I saw that some of you already have some experience with the OpenFOAM. Sometimes OpenFOAM is not as much forgiving as a finite element software that we might be used on the structural side. I come from a structural engineering structural background originally, and where I was doing solid mechanics originally, and sometimes finite element software would still spit out a result. I mean, the accuracy and correctness of this result is slightly, let's say, another issue to discuss. But sometimes OpenFOAM or CFD softwares can be a little more finicky when it comes to the kind of a mesh that is there and all these aspects that are there. It might not even run, and it might end up giving you cryptic messages as to hey, think about this thing or something like that, and not really say, here is your error, kind of, right? And then it kind of starts to get really frustrating, and that is something that is experienced by a lot of students and researchers who are starting out with OpenFOAM. And I just want to say that because if you're feeling that, you're not alone there. There's a lot of people in the same boat, and I think that is where the SimCenter and through the HydroUQ, we are trying to do a hand-holding in there, and through the user forum, we are trying to give us a constant support where we try to answer each of these questions on a workday within a 12-hour, or probably as soon as you send it, if we see the message, which will send us an email notification, we try to answer it immediately, or if it's on a weekend, probably within a 24 hours, we try to get back to you. So there's a lot of hand-holding in terms of the what we are providing through the SimCenter, and I don't think there's a need to get frustrated when CFD simulations are not working. The most important thing I want to say, it will not work a lot of times, and that's kind of something that happens a lot, and that's where we are here to kind of help you with it. So just to give you an outline of the training that and the discussion that we are going to have in the next couple of days, while I'll talk about the installations and accounts, we will go about it in detail, try to see that, make sure that everybody is has checked that box, has it in design safe account. Maybe probably if you want to have a GitHub account, and then you're install the HydroUQ and it's working well, and how to fork this, how to make sure you have the latest update and development. I'll walk you through each of these things, even though many of you might have already tried out, just to be sure that everybody is on the same page. Then in this session, we'll look at what is HydroUQ, how it works, and particularly with regard to the coupling with shallow water solvers, particularly GeoClass. Why do we want to do this coupling, and what is the reason for this thing? Then in the next session, we will try to set up, our goal is to basically set up one single simulation with HydroUQ and be able to run it. I also have a small Jupyter notebook that we can work through to try to see and extract the data from a GeoClass simulation solution, so that we try to understand what is GeoClass giving out and how do I export this information into HydroUQ. I mean, technically, when you use the HydroUQ, you don't have to do this manually. HydroUQ does this for you. But we will take one step back and try to use the Jupyter notebook to see what HydroUQ is doing, so that we understand what is happening in HydroUQ. And this is where I want to open up a researcher component and try to highlight some of these researcher modules that we have, where you can come up with your own Python modules and just send it into HydroUQ. So you don't have to use the module that is always there in HydroUQ, but as a researcher, you might want to do new things. That is how does HydroUQ help you with it? That's where kind of I want to bring this session in. And today we'll be ending a session, ending the day with a session by my colleagues Sandri and Akash, who will be talking about uncertainty quantification. So most of us would have heard of this UQ, machine learning, AI these days. Like these are like the buzzwords out there. So essentially, like if I would put crudely what UQ would be, let's say if we say steel property is 210 GPa, right? Young's modulus is 210 GPa, but it's not always 210 GPa, it's always plus or minus something, right? So now how does this plus or minus affect the overall structural response in a way, right? So steel is just one material property, one example, but there can be several things in there. For example, let's say when we take the fluid, if there are debris in the fluid, that can change the viscous properties of the fluid and so on and so forth. At the moment, UQ is still primarily on the structural thing, and we are trying to bring it to the fluids. But this is just an example of what the UQ would be and how you would account for these uncertainties in the structural response there. And tomorrow we will try to use HydroUQ to set up a wave flume. And this is where we will also try to run a whole bunch of different simulations, because by tomorrow morning, I'll hope that you already have played a little with the HydroUQ, you have installed it, it's running now, you already did one simulation. So we'll try to explore more aspects of it and try to see what is happening out there, right? And primarily, like we have also worked with the Oregon State University, thanks to Pedro and Tori Johnson and Dan Cox and Pedro from OSU, and Tori Johnson from US Naval Academy, and we have been working with them. And we have been able to set up a digital twin of the Oregon State University. So we will see later that you can just select, hey, standard OSU flume, and rest of the simulation is just like, you don't have to worry about the geometry. Geometry is automatically set in there. So we'll, and there's a moving wall that replicates the flume moving wall, and how does this happen, and so on and so forth. Finally, like one thing that is there in the HydroUQ is you'll find a box that says upload OpenC script, right? So unless you're coming from a structural engineering background, you've used OpenC, you'll be wondering, like, okay, what is this OpenC script, right? So that's where Quanchi would be really, I think Quanchi is also here now, and he would be talking to us about OpenC and how to set up the script, like, how to set up a building model, what is the OpenC script, and how do I import it into HydroUQ, right? So this is a kind of like overview of the entire thing. And finally, before we close up, I'll talk about the post-processing in HydroUQ. So if you already downloaded, try to run it. If you try to use post-processing today, it will not work because I disabled it. Because we want to go one step at a time, try to understand each of these features, because a lot of them can be very overwhelming. So kind of make sure we understand each of them, go one step at a time, right? So tomorrow we'll also be looking at post-processing. There's a post-processing for the structures, but how do I get for the fluids? I want to probably get velocities and pressures at different points in my flow. How do I extract this data as well? Right. So we are also working on more post-processing scripts that we'll be talking about later. So that's just a general idea. And one thing that I want to really stress upon is the office hours that we are holding every 15 days, right? So these office hours are again, like since we have the HydroUQ tool training today and tomorrow, the office hours automatically follow on the Friday, and you don't have to register separately for that. But if you are on a general day, you will have to register for these office hours in order to join them. I just made a short link of the office hour link for the registration page. You need not do it for this Friday, but 15 days from now on, if you would like to join in, you would probably have to register. And this office hours gives you an opportunity to sit with us and talk to us and bring out your concerns. Okay, I'm trying to do this thing, and hey, I'm stuck here. How do you help with? Can you help me with it? And if we can set up a separate meeting, even if it's a longer discussion and we can set up a separate meeting, I would be happy to sit with you on a Zoom call and try to get you through the simulation and make sure that everything's working for you and help you with it, right? So this office hours gives you a chance to come and talk face to face on a one-on-one basis with us too. And we also would like to know what you're doing and how we can help you with it, right? So just a general motivation of like, I mean, I don't think any of you are new to coastal hazards, but I think I just want to kind of motivate the topic as to why do we want to do the simulations the way we are doing it, right? So, I mean, most of you also already also know about the 2004 Indian earthquake, where about 250,000 people were killed and many more were displaced because of the earthquake in Indonesia, and then further followed tsunami, which also led to a lot of damage. So one thing that was significantly noticed that was that there's also severe damage to the ports and coastlines, but the speeds were relatively less. But then there was still a lot of damage that occurred during these tsunamis, right? And same thing again in 2010 tsunami. This was a image of the port in Chile that happened during the 2010 tsunami in Chile, where some of these shipping containers were almost displaced by about 500 to 300 to 500 meters in a way. So, and then when the ships were like tied together, they were dragged in together. So there was a lot of drag force. In spite of the velocities being really less, the mass is very large. So there's a huge amount of momentum that kind of, when these ships come in and impact, they can cause a lot of damage to the structures, right? And also, like same thing happened in the Tohoku tsunami. I mean, I heard from Pat Linnett that relatively unknown event was in I think the Guam port in Japan, where there were like nuclear submarines that were parked in there that had literally started to rotate during the tsunami. And so, I mean, these can be like pretty scary events that would happen in there. I mean, we hope they don't happen, but then we need to be ready for them, and we need to understand, and we need to take care of them. So one of the things that came out of a lot of these studies that happened over the years was that yeah, somebody there's a question asking if we can get a copy of these slides. Sure, we can definitely try to make that available to you. That could definitely be made available. I think should be possible. One thing that again coming back to it, like one thing that was noticed during a lot of these studies that happened was that it was always difficult to do a horizontal evacuation, right? So people trying to flee from the places of tsunami, many of them got stuck in it, and especially during the 2011 Tohoku tsunami. And one of the ideas was, okay, during these events, can we build vertical evacuation structures so that people can take refuge until the tsunami passes out in a way. And so that's the kind of one of the motivations to also during the storm surge, for example, if you're looking at an oil rig of Hurricane Katrina, which is in 2005, which was completely damaged. So the whole idea is like, can we build these kind of vertical evacuation structures that can be used for people to take refuge during some of these events that happen, natural hazard events, right? So we want to try to build structures that are resilient, and we want to understand their structural response alongside the inundation depths and fluid velocities and so on as well. So kind of it makes a very interdisciplinary problem. So if we look at generally our civil engineering departments, we are like either in a structure that there's a structures group, there's a fluid group, which is looking at the environment, but then there's more of like a kind of a multidisciplinary thing or interdisciplinary thing that needs somebody to understand the structures and the fluids as well, which makes it super complicated to address both these issues, right? So that's one of the motivation for the HydroUQ tool, where somebody coming from a structural engineering background can use their background to build the structural models, but can easily use the CFD part of the tool to run these simulations, get more accurate load on the structures to get the responses. Or somebody who's coming from a more fluid background can use the structural part of it a lot more easily using some of the MDOF models and so on. And they can use this to also try to do a structural response and look at the whole problem holistically rather than just one part of it in a way, right? And it's not just the fluids that is coming in, there's also a lot of debris coming in, there's a lot of erosion that's happening. So there's an environmental part of it as well. And that's where we are trying to bring the CFD so that we can look at local community level events that are happening in there. And but then also try to understand the whole picture. So this picture kind of is what depicts what the HydroUQ tool does. People ask me like, oh, is the on the right side, what is it? Is it a flume? So that's where I'm kind of trying to bring, it's like the image is kind of like bringing a double message in there. One thing, we can do a multi-scale modeling. And second thing is that we can also do we have digital flumes that you can use for experimental setup in a way. So it's kind of conveying two of these images. And you can look at the structural models, build structural models and get a uncertain and let's say probabilistic response. It's not like, okay, my deformation is 0.01, but it's like 0.01 plus something, plus or minus something. So there's a variance, and this is my stress and there's a variance of this. That's what we can get out of the HydroUQ tool. So the whole idea was basically when the community, there's a lot of big part of the community that is using shallow water solvers, and these are really nice. I mean, and we are just talking about GeoClass. We are also working with AdCirc as well. So there's a lot of community using that, which gives a very good big picture idea. But now I want to look at the local building level. So we want to resolve them using much high fidelity tools with CFD and finite element, and look at the structural response and kind of couple all of these different tools seamlessly. That's where HydroUQ is coming in. If you think about it, on one side we have the shallow water solvers and the like the GeoClass and the AdCirc. Then we have the open foam or the CFD. So for example, tomorrow you say, hey, I don't want to use this open foam, but I have my own CFD solver. HydroUQ is built in such a way that you can just remove open foam and put your solver in there. That's where I'm going to highlight the researcher modules that we have in the next session. And the third part of it is like the structural part where we're bringing the open Cs, and the Dakota, which is bringing in uncertainty quantification engine and so on, and trying to seamlessly couple all these things. So even though I'm not an expert in UQ, I can probably go there and I think I can select reasonable number of methods and try to see what's happening out there, right? So that kind of gives the flexibility with the HydroUQ that is not available with most of the other commercial tools. So let's try to focus on the coupling with the GeoClass. I mean, I don't think I can explain GeoClass as better as Professor Levack, who is also here. And I think the best, I mean, I also would probably, I think later I have some couple of links where I would be talking or giving you some links about some of the really nice tutorial videos that have been done on GeoClass and also the theory of GeoClass. So I'll try to keep it simple to just some basic equations so that we have an idea of what we are talking when we say shallow water solvers, right? So just to make sure. So for example, when we are trying to model a tsunami event with the GeoClass, so what we do is we kind of take some kind of a source, a slip distribution, like an initial condition. It's okay, where is the earthquake happening? How much did it happen? And how much did, let's say, the water move, or the column of water move, to say in a more crude way. And that kind of gives us the initiation condition for this wave propagation over long distances. So, I mean, just to give you an idea, so this was a work done by, in collaboration with Professor Patrick Linnett at USC by one of his students, Bezad. So this is just giving you an idea of the earthquake on Alaska fault with I think Cascadia and Hawaii being the areas that we are resolving into. So, for example, if you look at it, you can see that there's a mesh around California, and there's a small mesh around the Hawaii, which is much more resolved than the larger mesh that is where we are running these tsunami simulations with GeoClass. right? So now we want to take these smaller mesh and we want to try to build a much smaller and more high density, let's say, mesh there to do a full 3D CFD simulation, right? So what is the GeoClass giving us? It's giving some kind of a depth average velocity. So we'll look at some of these equations as we go on, but what we have is essentially like a average of the velocity over the entire depth. So if somebody is coming from a structural background, is something like connecting the GeoClass to the CFD software is something like connecting a beam to a solid in a way. So you might have used beam elements, you might have used solid elements in finite elements. So how do I connect a beam to a solid, right? So that's a similar analog here. How do I convert a depth average quantity into a full three-dimensional field? So I'm adding some information in there. So that opens up a lot of possibilities of how it can be done, right? So we have done it in a particular way, and that is what I would talk in the next session, and how you can try to bring in your own ways of doing these things, and that opens up a research possibility in there, right? So just to give an idea of the shallow water assumption, essentially is that the depth of the water is the ratio of the depth of the water to that of the wavelength is much smaller than 1. And essentially here we can use some kind of approximation to ensure that the shallowness is satisfied. But what happens as these waves propagate and come near the coast is that these let's say you imagine that the wave is coming in towards the coast, then the depth starts to decrease, which means that the energy has to go somewhere, right? So the amplitude of this wave starts to increase while the wavelength starts to decrease while the amplitude starts to increase as they near the coast. And then we probably want to use some kind of a nonlinear solvers that are nonlinear shallow water equations in order to ensure that we are correctly capturing these phenomena. And so that's where we are kind of trying to bring, once the wave comes near the coast, use a full 3D CFD simulation in order to capture the entire event in a way, right? So what is the depth average equations? Essentially, let's start with a simple Navier-Stokes equation. I'm trying to put these equations in there because we want to just remind ourselves about what we are trying to do here. And I'm not going to go into detail of the theory. Like in a couple of slides, I have these really nice links to some of the YouTube videos that are there, particularly by Professor Livak and his students, who have really explained GeoClass and the depth average equations really well. And I don't think I can do I can do anything near that, right? In the time we have. So if somebody is interested, I would definitely ask you to look into that. Right. So we have this Navier-Stokes equation, and what are we trying to do? Let's say, for example, to start with, let's assume a simple problem where we have like a flow along one dimension in a way. So we neglect the y dimension. So let's say x is the direction of flow, y is perpendicular to it. Let's say I neglected like some kind of a channel flow kind of a thing. So there's a depth in the channel, right? So we can write this Navier-Stokes equation. I'm just expanding it and writing from the tensorial form into like a completely expanded form, right? And so what are the boundary conditions? So we have a free surface and we have a bottom surface. So one could say that, the bottom is like a no slip condition, which means that the velocity, normal velocity at this bottom surface is essentially 0. And the velocity also normal to the top surface is essentially 0, right? So I can kind of make this assumption, and the pressure at the top surface is 0. So I make some of these assumptions, and then what I would do is I would basically integrate it over the entire depth. Right, so B is my bottom, B to eta. If somebody is interested in deriving them, I would be very happy to sit with you to help you with it. But I just want to make sure that you've seen these equations when we try to, before we go into the next session, to understand how this multi-scale coupling is happening in there and how you can think about it, right? So essentially, if you're doing an averaging, instead of U and W now, so W vanishes. And instead of U, now we have U bar, which is nothing but the average of the velocity over the entire depth, right? So we have some kind of a U bar into H, which is nothing but the height of the water column. So this height of the water column is changing because also our bathymetry is continuously changing, and also the wave is moving. So height of the water column is changing. Okay, the bathymetry is changing over X and Y, but then the let's say the height of the ocean surface is changing with time. So which means that the height of the water column at any point is changing with time continuously because now there's a wave propagating. And so essentially what we have is this depth average equations where we have some kind of a rate of change of the height, which is the rate of change of the water column, and the rate and the spatial change, the gradient of this h into u bar quantity as well, right? So I just want you to have a look. I have an understanding that, okay, these are the equations that we are starting. So that is what our GeoClass is solving for us. So essentially when GeoClass solves, you'll see that the solution files has 4 columns. So one of this column, first column would be essentially the height of the water column. The second and third would be the X and Y momentum, which is essentially something like H into U bar and H into V bar. And then the eta, which is nothing but some kind of something to do with the bathymetry plus the height, or the bathymetry plus the depth of the water column. We'll exactly see what it is as we go ahead. But just to give you an idea, where is this HU bar coming and where is this H coming into our solver as well. So I just want you to remember these equations that is marked in this red box in there, right? So we will try to look at them again. We'll come back to look at them. And again, there are some assumptions that are further made and things like that, which I will not be talking about it because going into these will take us in a completely another direction. And in a way, I don't think I'm the expert in the shallow water solvers. I'm not expert with the shallow water solvers, but I would leave it to the experts as such. So if somebody wants to make sure of a link or take a screenshot, then I'll probably leave this. So there's like really nice tutorials on how to run GeoClass and how to run like what is happening in there, how to run GeoClass for storm surge, how to run GeoClass for tsunamis. Also, like there's like this three-part video that I really found on the GeoClass theory as well, and looking at the partial differential equations. I would probably just leave this slide up for a couple of for a few seconds, so that if you would like, you can take a screenshot of it. I would definitely share the slide deck as well so that you can go and watch. And they're really nice videos. I mean, setting up GeoClass was like really easy. One of my intern RU students, she's working on GeoClass. And some of the data that we will be using in the next session is generated by my student. She did a really nice job, and she's working on a compression algorithm in order to compress some of these large scientific data into smaller space. It was really very easy. She just followed these videos. So this was a set of videos that I had earmarked for her. And she was just able to like look at the video and set it up using Docker, and it was super easy to set up GeoClass. There's some really nice work done there in order to get people running with GeoClass. So, I mean, this is just to give you an idea. So if you want to run a multi-scale simulation, want to have your own GeoClass simulation, apart from the data that I would be sharing later, I just want you to make sure that you have the resources that you can go back and see how to run the GeoClass simulation. Right. So, okay. So coming back to our motivation of multi-scale modeling, we saw a lot of these things. So as we saw this really nice simulation over the earthquake globe that where the earthquake happened in Alaska fault, and there's all of these waves that are propagating, which are the tsunami waves coming into Crescent City and Honolulu, right? So our goal was like, okay, if you want to now, if you think about the length scale of it, we are looking at like tens or hundreds of kilometers, right? And now if you look at a building, we are looking at a building scale of few meters, right? So now if I have to resolve my grid to really small extent, then that's going to take a lot of computation time. GeoClass has a really nice automatic mesh refinement and everything, but we want to it's much easier maybe to just take these results and try to set up an open form simulation, and I'll be showing you how to do that as well. So here, just the idea is essentially we have this GeoClass domain, which is, for example, here where you're seeing there's a fault or a low pressure zone. So if you're coming from a tsunami background and you're looking at a fault from which there's an earthquake, or if you're coming from a storm surge background on the East Coast, then you're probably looking at a low pressure area from which there's a storm surge that is propagating. Now there's, for example, these orange boxes are essentially something like our building of structure interest. So for example, this can be an oil rig in the middle of the ocean, or this can be some kind of a structure that is there on the coast and that we want to study. So these are like some kind of a critical infrastructure, or these can be like vertical evacuation structures that we really want to understand how these are working in there. So what is the HydroUQ doing? HydroUQ essentially is like taking our shallow water solutions. So for example, here you can see, so this is probably going to be my only slide. I'm not much of a presentation person. We'll be doing a lot of writing and trying to look at the tool itself and looking at a lot of these things, but just probably these pictures kind of convey the idea much better in a way. So I have this in them. So on the left side, you can see that maybe there's a pointer or something. Let's see. Okay. Oh yeah, on the left side here on the bottom side, you can see there's something called 2D shallow water solutions user input. So when we are doing these multi-scale simulations, we already have these pre-run GeoClass solutions. We bring this as our user input. And what HydroUQ does, it has a universal interpreter that is trying to read these solutions and set up a CFD simulation with OpenFOAM. So essentially, when I mean setup, it helps you to set up the boundary conditions, and it also helps you to set up the geometry. Of course, when I say it helps, we have to also do a little bit of work to give the information in the right format and place. But once this is given in, it creates a 3D CFD files, which is essentially the OpenFOAM dictionaries for the simulation. And once the CFD simulation is done, and then this automatically the forces on these buildings are recorded, or the pressures on these buildings are recorded, and they're passed on to OpenSeas in order to do a structural simulation. So in a way, the coupling at the moment is a one way. And when we do these 3D finite element simulation on the structures, we also account for the uncertainty quantification, or the UQ part of it, where we can look at different material properties, different various variations in the structure in order to see how the structure would respond because of these variations. Of course, we are also trying to bring in this UQ into the fluids part. Probably in the next version, we'll try to have that in there. But one of the challenges of the CFD simulation is that it takes a significant amount of time, right? So for example, let's say we did a simple wave flume simulation where basically, like, if you have seen this wave, if you just Google out wave flume Oregon State University, you'll find this really nice experiment. So you have a wall that is moving on the left side, and it is generating huge water waves, and there's some miniature structures, or like kind of, let's say, scaled down structures on the right side, and the researchers are trying to understand how these waves would impact the structure, and kind of let's say what can be done to make them better, right? So if you once a very coarse mesh of the simulation can take about 20 hours or so, and then again post-processing the results and so on, the overall time takes about 20 to 30 hours. And now if you imagine that you want to do simple Monte Carlo simulation, you want to just run this simulation 10 times, that's like 300 hours, or probably you can put them in parallel, right? I mean, you can probably do it 10 of these simulations, but then it costs a lot of time both to pre-process everything and post-process everything and to run these simulations. So that's where we are trying to bring the UQ part, where UQ will be able to intelligently choose what are these 10 simulations that I want to run, so that I'm able to generate a reasonable surface to create 100 simulations that can be run faster, right? So that is something we are looking up in the next version of it. But for now, what we have is a really nice universal interpreter that takes in the GeoClass inputs and tries to put them into the OpenFOAM, right? And tries to run things there. Right? So yeah, like I was talking about, at the moment, we do not have a two-way coupling between the 2D shallow water and the 3D CFD domain. There are a lot of work that have done these 3D coupling, so we are not the first out there. There are people who have done a 2D coupling, two-way coupling between even with OpenFOAM and other aspect as well. But at the moment, we are still doing a one-way coupling for multiple reasons. And we would be very happy if somebody would like to do a two-way coupling, and kind of we would be very happy to help you with it and as well. So at the moment, essentially, like, you take the shallow water solutions and you impose some kind of a boundary condition on one of these patches on the CFD. So what is the drawback of this method? I mean, I'm not going to say that my method is a perfect method. It's probably really flawed, I would say, right? So that's where, like, there's a lot of potential where new things can be done in there, and new stuff can be added in there. So essentially, one of the things that is the biggest problem is, for example, let's say you have a wave propagating. Now you have a wave, let's say after it hits a wall or something, now the wave starts to reflect back. So once it starts to reflect back, the problem is you don't have an outlet. So let's say your patch has an inlet from the shallow water domain into the CFD domain, but it does not have an outlet from the CFD domain into a shallow water domain. So what is going to happen is if your domain size is not reasonably large enough, once you have the wave going in and coming back, you would have an artificial accumulation on the boundary where you have the shallow water solutions. So this is something that we understand that is a drawback of the method, and we need to keep in mind when we are choosing how much time do we want to simulate and what is our domain size. Okay, so think of a simplistic way would be thinking about it is like, what is my wave velocity and how much time would it take for it to, let's say, have a reflection and come back to the same surface, right? So now this is essentially this velocity and would define how much time you can simulate this for. Because beyond a certain point, once the fluid starts to accumulate on the left side, then essentially your simulations are wrong from then on. And so we need to be careful and think about how we set up our simulations. So the whole idea of this training would be to focus on how do we set up these simulations in a correct way. So once the open form simulation is done, it gets the fluid force on each of these floors. And what is going to happen is going to try to get the deformed shape of the building. So again, this is one way, but then we are working on a two-way coupling for this thing. And if somebody is interested, we would be very happy to work with. Right. So what happens here when we are doing the coupling from the shallow water domain into the CFD domain? So first thing is we want to, let's say if we think on the left side, let's say if we look at this figure on the left, here we have just like, think of it as like we have 1 point. But on the right, on the neighboring, let's say on the boundary between the 2D and the 3D, on the 2D we have 1 point, on 3D we have, let's say, multiple points. So the information from 1 point needs to somehow be populated into multiple points. So it's not a one-to-one mapping, but it can be a one-to-many, not a one-to-one mapping in a way, right? So that kind of creates a complexity and also an open thing that where we can do different kinds of problems. So one thing that we simply said, or probably our fluid profile has some kind of a logarithmic profile with regard to the depth, right? So it's not a very bad assumption. There's a lot of geological flows where people use this kind of an assumption, and it's reasonably assumed to be correct, right? So and then what we do is we try to have a corrector in there in order to ensure that the mass and the momentum are conserved as well. So this is what happens in there. So we are taking some kind of a 2D velocity and converting them into 3D velocity depending on the depth of the flow of the domain, right? And so there are the various parameters that are there that are essentially figured out in an empirical fashion, like the friction velocity and the von Karman's constant and so on and so forth. But this is something that we would be looking at and see if this is not the most perfect method to do this 2D coupling from the shallow water into the CFD domain. But we would like to see what are the other ideas that are out there. How can we do it better? What can be done? And so that's a researcher module that is available where you can, if you have an idea of how you want to go from 2D to 3D, you can fill up this Python script and try to see how your method works against the standard method that is there in the HydroUQ tool, right? So so again, this is where I want to highlight. So for example, if you go into the documentation, there's something called a shallow water CFD interface where you can find this kind of a Python script that is there with some classes that are available and some definitions that are available. So essentially for somebody who's not coming from an object-oriented background, then essentially this is nothing but your functions, like in a MATLAB function that is available. So you can just fill this function to read. How do you read the bathymetry? I'll probably already have a script on the Jupyter notebook later in the next session. Or how do we read the interface? How do we read the solutions? And then how do we convert this boundary? Right. So we'll probably do all of these things in the next session with the Jupyter notebook so that you get an idea of this kind of a researcher module or a Python script that you can bring bring your own custom components into HydroUQ. Because I don't want to say that HydroUQ is a tool where you just you put something and you get something out, because that's not useful for researchers, because we want to do something new. We want to understand something better. Maybe either you're understanding from a physical point of view or developing a new numerical method. Most of us are writing scripts, either small scripts, large scripts. Some are running on supercomputers, some are running on our local computers. And so that's where I want to introduce that these kind of scripts can be added into the tool and can be used in there, right? Okay, so I think we are almost at the end of the this session. So I just want to go over the logistic, but we'll go over them in detail. I think Matt already suggested about talked about the user forum. So there's a hydrodynamic engineering forum there. So if you have any questions, please go and post it there. We are very happy to answer it. And if you say, for example, hey, I'm trying to do this thing, and can you help me with it? So we definitely encourage these kind of questions, and we want you to give the feature request in sense like, I was trying to do this, I don't see this thing available in the tool. Do you think you can add a module for this thing? We would be very happy to consider that and try to work on that, right? So of course, depending on how big a request this is, this can take quick, probably a turnaround in half a day, or this can probably take a turnaround back in a month. But again, that depends on the request that you're making in there, right? So, but then we are very happy to do it, and we'll, depending on what you're asking, if it takes more time, we'll probably sit with you and try to see how we can help you with it in the immediate future as well. Right, on a work day, the questions are answered almost immediately, and on a weekend, probably or on a holiday, probably it takes a little longer if we are not in front of the computer to try to get back to you and try to answer these questions. But I want to emphasize on this because when you're trying to do a CFD simulation, things will not work. There'll be a lot of errors that you would be getting, and that's where probably please post these questions so that we can help you with it rather than you having to struggle with the cryptic messages out there. OpenFOAM can give a lot of cryptic messages, trust me, and you don't have to worry about it. We are there to help you with it to make sure that your simulations are running out there, and that's what we are doing there. And I saw that anyway, most of you already have a DesignSafe account. So if you don't have a DesignSafe account, I think a couple of you had not registered. So please register for an account. It's free, irrespective of whether you are in the US or whether you are in any other country. It does not matter. There's a DesignSafe account is for free and almost nearly unlimited computing resources. I don't know if there's actually a limit on how much you can use, but and if somebody's tracking it, but there's almost unlimited resources for if you're doing natural hazards research. And I think the storage space you get is about 50 GB or something, and that's reasonably really nice. And of course, there's simulations that can take longer, but then and all of these things, any simulation you run is on our allocation, but you just need an account to at least log in to even to use the HydroUQ tool, right? For those who have not already downloaded the HydroUQ app, sorry for the inconvenience. So if you go to our HydroUQ webpage, I sent you the links a little while earlier, so that I can repost this link again. So there's a folder called old versions, and the new version has been put into it. Unfortunately, our engineer is on vacation in Ireland, and I don't want to disturb him. Because if to get him to do this, because he's the only one who has access to be able to do this. So unfortunately, the new version is in the old versions folder. I just sent you the link also on chat. So please do download the latest version. If you can see, the version that you're downloading should be updated on the July 20th or 20th of July 2021. So if you're on Windows, then it's reasonably straightforward. Download it, unzip it. The app should start working. If you're on a Mac, then probably you have another step that we need to do a pip install, and I'll come back to it. I'll probably leave it in the break so that you can kind of try it out. So if you're on a Mac, try to install Python 3.8. If you have Python 3.9, then there is a problem because the tool doesn't work with 3.9, so you would have to also install 3.8. So these Python versions are changing so fast that it's really hard to keep up with them at times, and there's a lot of compatibility issues. So we are fixing our tools to a particular version so that it can work on anybody's computer. So you just have to open up your terminal and type pip install neri-simcenter. That is going to install all the modules that you need in order to run our tools, including the backend application and so on. I'll talk about what this backend application is, what is this cryptic thing. So please download the HydroUQ application so that by the next session you already have it installed, and then we can again start using it and try to run some simulations with it, right? So I'll leave this slide back on. I don't think, yeah. And if you, yeah, so this is probably my last slide for the session, and I think we are pretty much on time here. So if you'd like to, please go and fork the GitHub as well. So for example, if you just go to GitHub, if you can see the link here, Neri Sim Center HydroUQ, you can, once you fork it, you always keep a copy of it. Even if we delete it, we are probably not planning to delete it, but even if that happens, you will still have a copy of it. Or if you just start it, you'll also be able to follow some of the notifications when there's a new update. So generally an installer is made out once in a month or once in 2 months when we have sufficient number of patches. So if you want to have the latest version, please download from the HydroUQ GitHub, just fork it. And whenever you need to, you can always install it and try to run the latest version, which might have more patches than what the installer has at all times. But then I want to ensure let you know that whatever is on the GitHub is the latest and it's always working. So probably there's a fork of mine where I'll be working on things and probably there'll be things that don't work. But anything that is there on the Neri Sim Center HydroUQ page is something that will always work. So if there's something that's not working in, please let us know on the forum and we are happy to help you with it. Or if you're not able to install that. So please do go to the GitHub account and try to fork it so that you have a copy of it. And it's I'll also show you how to get the latest version. It's just click of a button, just click up, get upstream, and you have the latest code and you can always work with it, right? So I'll leave you with this particular page. So for anybody who wants to install, for those who are on Windows, it is super simple. Just download the installer and just unzip it. And then you have everything in there. Just you don't have to worry much. But for those who are on Mac, you just need to run this command pip install Neri Sim Center on the terminal. And once this is done, then essentially you have all the backend applications. So these backend applications are packaged with the Windows. So that's why if you look at it, if we go back here somewhere, if you can see, so the size of the Mac installer is something about 130 MB, but that of the Windows is about 380 MB. So that's almost about 3 times the size, because whatever you're doing pip install on the Mac is already put into the zip file when you're downloading. And that is the reason why it is so big. So please ensure that you have the latest version that is updated on the July 20th of the HydroUQ, and then I think we are ready to go for the next session in there.